Hello everyone, now we'll be discussing about the crystallinity and amorphism. So the crystal habit and the internal structure of a drug can affect the bulk and physicochemical properties which range from flowability to its overall chemical stability. So what is habit? Habit is the description of the outer appearance of a crystal, or the morphology of a crystal form is defined as its habit. Now coming to the internal structure is the molecular arrangement within the solid. So both this crystal habit and internal structure, they can affect the physicochemical properties of the drug. And a single internal structure for a compound can have several different habits. Single internal structure can have different morphologies depending on the environment for growing crystals. The example is spironolactone. It is a diuretic. It exists in two forms, form 1 and form 2. So form 1 is needle type and form 2 is prism type. One more difference is the form 1 spironolactone, it has a melting point of 205 degrees centigrade, whereas form 2, which is prism type, has 210 degrees centigrade. So a single internal structure for a compound can have different habits, several different habits. In certain cases, as in the case of conversion of sodium salt to its free acid, it results in the change in both internal structure and the crystal habit. Usually the internal structure remains constant and there will be different crystal habits, but in some cases such as conversion of sodium salt to its free acid, there are changes in both the internal structure and the crystal habit. So whenever we consider a new compound, identification of the solid form is necessary, and it involves the following steps. First, verifying that the solid is the expected chemical compound or not. The second is characterizing the internal structure, and the third is describing the habit of the crystal. Now coming to the characterization. So chemical compound has an internal structure and a habit. The internal structure is further divided into, it can be either crystalline or amorphous. The crystalline internal structure is further divided into, it can be that particular chemical compound be a single entity or it can be a molecular adduct. Single entity example is polymorphs. Coming to molecular adducts, they can be either stoichiometric or non-stoichiometric. Non-stoichiometric molecular adducts are also called as inclusion complexes. They are of three types: cage, type, layer and channel. The next molecular adduct is stoichiometric adducts. They are either solvates or hydrates. So this is the overall classification of chemical compound. Now as we have discussed, the internal structure can be either crystalline or amorphous. So when the internal structure is crystalline, there exists a repetitious spacing of atoms or molecules in a 3D array. The atoms or molecules are arranged in an orderly manner in a three-dimensional array. When it comes to amorphous internal structure, the atoms or molecules are randomly placed in the liquid. That is the basic difference between a crystalline internal structure and an amorphous internal structure. Coming to amorphous forms, the amorphous forms are generally prepared by rapid precipitation, lyophilization and rapid cooling of the liquid melts. And since the amorphous forms are usually of higher thermodynamic energy than their corresponding crystalline forms, these amorphous forms, they have high solubilities and dissolution rates when compared to crystalline form. Because of higher thermodynamic energy, they have higher solubility, higher dissolution, and as a consequence, they have higher bioavailability. And one more important point is the amorphous solids are called as supercooled liquids, in which the molecules are arranged in a random manner as in the case of liquid state. When it comes to solid state, the molecules are arranged in an orderly manner. But when it comes to liquid state, the molecules are arranged in a random manner. So, even in case of amorphous solids also, as the molecules are arranged in a random manner, these amorphous solids are called as supercooled liquids. And one more important point is they differ from their crystalline solids in such a way that they tend to flow when subjected to sufficient pressure over a period of time, and they do not have definite melting points. They tend to flow and they do not have definite melting points. The amorphous solids and the cubic crystals are usually isotropic. This is also one of the characteristics. Isotropic means they exhibit similar properties in all directions. Whereas in contrast, the crystals other than cubic crystals are anisotropic. They show different characteristics such as electrical conductance, refractive index, crystal growth, rate of solubility in various directions along the crystals. Amorphous solids are isotropic is also an important point. So coming to the overall characterization, they have high thermodynamic energy, they have high aqueous solubility, dissolution and bioavailability, they have low melting point and low stability, and they are also isotropic. Coming to the classic example of novobiocin. Novobiocin is an antibiotic. The amorphous form of novobiocin has a greater solubility and higher dissolution rate compared to its crystalline form. The amorphous form, it yields 3 to 4 times higher blood concentrations when compared to the crystalline form. And one more important observation has been noted in the case of aqueous suspension of novobiocin. That is, the thermodynamically unstable amorphous form converts slowly into the stable crystalline form upon storage. Whenever stored for a longer period of time, the amorphous form may tend to convert to the crystalline form, and this conversion results in the loss of therapeutic effectiveness of the dosage forms. Coming to the other examples of amorphous solids, they are beeswax and paraffin. Though beeswax and paraffin appear to be amorphous, they tend to assume the crystalline arrangements when heated and then allowed to cool slowly. Usually they look to be amorphous, but whenever they are heated and then allowed to cool down slowly, they assume a crystalline arrangements. Petrolatum contains both crystalline and amorphous constituents. Glass and many synthetic plastics and even ceramics are also amorphous in nature. Even glass may crystallize after long standing. Thank you for watching. Please subscribe for further videos on pharmacy.